Hi, my name is Alexander Bahrim, majoring in electrical engineering, with my two mentors, Dr. Gleb Tscheslavski, Associate Professor and Chair of Electrical Engineering, and Dr. Cristian Bahrim, Professor of Physics. My research is in the development and assessment of hardware model for studying the mechanism of regenerative braking system. Now, what is regenerative braking system, or also known as RBS? RBS is an energy recovery mechanism associated to slowing down a moving vehicle or object by converting its kinetic energy into a form that can be either used immediately or stored until needed as electricity. Now, what is the impact of RBS technology? It allows electric vehicles to reach range demands and benefit from all forms of electric motors to further help the environment by making EVs the transportation standard of the future. What could my research accomplish? Because RBS successfully allows one to regain energy in a car battery, I hope in this project to meet the minimum 16% energy regain limit for marketing the efficiency of electric vehicles. And besides being more efficient, electric vehicles will be more environmentally friendly and even capable of extending the single lifespan of a physical braking system. Two main goals of my research include fully building an RBS in our laboratory, a model RBS in our laboratory, to study the optimum capacitance and resistance combination in the system to achieve the highest efficiency possible. And through my experimental results, my system will demonstrate the functionality of an RBS to meet the critical efficacy desired for the automotive industry. The materials for this project include a CPM integrated servo motor, which is a DC brushless motor, which is used in my model RBS. This motor came with a power supply and a ClearPath software. The ClearPath software allowed me to select the desired RPM for my system. The other software I used was the Analog Discovery Kit using the oscilloscope function to allow me to study the AC generator voltage. I also used a PMSM motor to perform as a generator in my system. I used capacitors, a rheostat, a resistance box, and a switch. I also used a flywheel, a diode bridge, and multimeters. The two images on the left, the one on the left and in the middle, shows a PMSM motor, which is then used as a generator, which will be referred to as a generator. And in the middle, we see the brushless DC motor in combination with the power supply. On the right, again, we see the ClearPath software, which allows me to select the desired RPM for my system. This is a schematic system drawing of the model RBS that I built. In phase 1, we see the power supply and motor, which powers the flywheel, allowing it to have kinetic energy, which is then converted into electricity by the generator, which is sent through the diode bridge, through the resistance, through the resistor box or rheostat, to then be captured by the capacitor. This is an overhead image of the actual model RBS that I built. As we can see, on the left side, we see the power supply and motor, which is used in combination with the generator with the flywheel in between. And the bottom right corner, we see the rectifier diode bridge, which is then connected to the capacitor, switch, and resistance box, which with the multimeters allows us to see the voltage captured in the system. This is another image of the motor flywheel generator system that I had built. In this video, we can see the model RBS in action with the oscilloscope connected to the very end of the generator. The oscilloscope allowed me to study the sinusoidal waves, which is then used to figure out the extinction time. Now the study. The shaft flywheel mechanism builds energy of rotation, which is given by the equation underneath, where F is the RPM in Hertz, and I is the moment of inertia for the flywheel with the two shafts on the motor side and the generator side. To calculate moment of inertia, we must first convert RPM into angular frequency. Then we must find the moment of inertia of the two shafts, and finally calculate the moment of inertia of the flywheel with the two chambers, R1 and R2. The making of the flywheel was done with the help of Dr. Gleb Tscheslavski, which allowed us to find a metal cylinder, which was then drilled and polished. These are a couple videos showing. The moment of inertia was calculated to be 0.003555 kilograms times meters squared for my system. Now, I had to calculate the extinction time using the oscilloscope. And the first test using the oscilloscope precisely allowed me to measure the voltage output from the AC generator and to study the sinusoidal AC signal and its root mean squared voltage value. The first 4 trials were done at 50, 100, and 150 RPM, and the voltage that was received was 13.36 on the oscilloscope. This turned out to be an issue because the oscilloscope I'd been using can only allow up to 20 volts. And so I had to figure out another way to calculate the highest voltage possible. And so, by using a multimeter, we were lucky enough to figure out that the values were very comparable. Multimeter showing 13.46 volts, slightly higher than the oscilloscope, but does allow us to safely use the voltmeter for reading the voltages. By using the 4 initial data points that we had, we were able to extrapolate this data to find the theoretical output of the motor flywheel generator system that I had built, which allowed us to figure out which capacitors to use later in my research. Now, this is an example of the signal from the AC generator before the rectifier bridge for a random case study at 150 RPM. The two curves correspond to the paired channels of 3-phase AC generator output signal. They are in sync as they should be, and this analysis also allowed us to diagnose test that the AC generator is functioning normally. We compared the extinction time with the characteristic time of the charging circuit after the rectifier diode bridge. The oscilloscope shows that the rotor of the AC generator has an extinction time of 0.42 seconds. This means that the characteristic time for the RC circuit, which charges the capacitor, must be much less than 0.4 seconds. Characteristic time is given by the equation R times C, where T 1/2 is the time charging for half the input voltage of the capacitor. In our RC type circuit, the complete charging of the capacitor is reached after 5 times that amount. In conclusion, the characteristic time needs to be short enough to avoid loss of voltage to the peak voltage, but not too short to not capture this voltage. The characteristic time should also be comparable with the length of the peak voltage. The 2 lessons that I learned from this study is first that the resistance should be small enough to reduce the energy dissipated in the circuit, and second, the AC generator produced about 2 to 3 oscillations in the AC voltage output to extinction, as one can see in the image before, but only the peak voltage is retained by the capacitor when it charges. The consequence of these 2 lessons is that the characteristic time should be decreased greatly as compared to my initial case studies. To decrease the characteristic time, we must decrease the resistance and capacitance in order to achieve the best efficiency. Finally, we reach the final trials. To start off my final trials, I tested the system at a capacitance of 1 and 5 ohms, at a resistance of 1 and 5 ohms, and a capacitance at 6,300 microfarad. After doing the calculations and running the trials from 50 RPM to 100, the maximum efficiency we were able to find was 11.35% at 5 ohms and 12.4% at 1 ohm. And although we observe a slight increase in efficiency from 5 ohms to 1 ohm, the values that we had were not satisfactory yet. So therefore, we chose to drop the resistance to a small 0.2 ohms to maximize the energy dissipated in the circuit. The result that we got from it was 12.31%, which did not show much of a difference at all, and it was within error of 1 ohm. As a result of these 3 trials, we decided to change the resistance, or keep the resistance, at 0.02 ohms, and use a capacitance of 12,600 microfarad, 3,250 microfarad, and 6,300 microfarad. The way we achieved 12,600 microfarad was to put the two capacitors of the amount of 6,300 microfarad in parallel. And then the way we achieved 3,250 microfarad is by putting the capacitors in series. With a resistance of 0.02 ohms and 2 6,300 microfarad capacitors in series, equivalent to 3,200 microfarad, we reached a maximum of 29.7% efficiency at 1,000 RPM for the system, which surpassed greatly the goal of 16% energy regain efficiency in my model RBS. By looking at the data, we saw that all the functions were parabolic, and as well, we can visually see where we reached 29% efficiency. Domestic cars typically run at 2,000 RPM, and from the best polynomial fitting function for a series combination of capacitors, we found that at 2,000 RPM, by extrapolating the data that we found that we had a maximum voltage delivered at 133 volts, which is 7.7 times more than at 1,000 RPM. And the efficiency that was reached was 51%, from about 30% at 1,000 RPM. And these numbers really encourage furthermore explanation on the implementation of these ideas in the car industry and implementing RBS into electric vehicles and electric motors. EV manufacturers and any industry that uses electric motors can take advantage of our findings and inspire others to utilize RBS in their applications. This research helped demonstrate that EVs and the EV industry can reach range demands, benefit all forms of electric motors, and further help the environment by making EVs the standard of the future. For my future research, I will try to 1. Use different flywheel combinations to change the inertia and optimize the flywheel placement on the shafts. 2. I will be using multimeters with faster response times, or use an oscilloscope that can go over 24 volts to view higher RPMs and study those sinusoidals, as well as increase the number of capacitors to more efficiently store the peak voltage from the generator in the RC system, thus increasing my overall RBS efficiency. I would like to thank Lamar University again for helping me with this research, as well as my mentors and all the staff. I would also like to thank the OUR Research for allowing me to have this opportunity and receiving the grant. Thank you.